My hope is that in this example, you'll be able to see the power of DeMorgan's theorem. DeMorgan's theorem is one of the most useful equations and theorems in all of Boolean algebra, and it can make huge, nasty-looking equations much, much simpler. And so here you can see on the left-hand side, there's this really big monstrosity of an equation with lots of these inverter overbars. You can see over here on the right, we've got 3 different levels of inverter overbars. And apparently it's claimed that this can be reduced down to a much, much simpler equation. You can imagine as an electrical or computer engineer, if you presented one of these 2 equations to your boss, you'd really prefer that it would be the much simpler one because that will be much easier for your company to build. So let's prove that the simpler equation will do everything that the big and nasty, complicated equation will do. The first thing I'm going to do in that process is I'm going to go ahead and duplicate this first equation. Now, I should mention in passing that these parentheses around the B and C are not strictly necessary. It turns out that there's a precedence of operations in Boolean algebra, just as there is in regular algebra, and it's the same as it is in regular algebra. In regular algebra, multiplication comes before addition, and if you think of the symbol for the AND operator being like the symbol for multiplication, and the symbol for the OR operator being like the symbol for the add operator, you can see that AND would come before OR. And in fact, that's exactly what happens. And so in the next step, I'll omit those parentheses, but for right now, I'll leave them in so that you can see that everything is exactly the same. So what I've got here is simply a repetition of the equation that appears on the line above. You might say, well, why did you bother to do that? That was a waste of time. Because now here comes the dual operation that represents what DeMorgan's theorem does. DeMorgan's theorem gives you the opportunity to break apart an overbar, and we always start with the longest overbar. So here you can see this one right here. That's the longest overbar. I'm going to break that one apart, and for now, I'm just going to represent that by scribbling out the middle part of this. So now I've broken that into 2 separate overbars. But you can't just do that. If you could just do that, then there would be no need for DeMorgan's theorem. DeMorgan's theorem says that if you're going to break an overbar, you also have to change the operator that lies between those 2 parts to the opposite operator. So you have to go from OR to AND or from AND to OR. And that's why I read you the equation so that I could scribble on it. Now if I redraw it one more time, I have A or... Oh, and I'll leave out the parentheses this time. A or B and C with 2 overbars, because the first one came from the original one right here, this original overbar, and then the second one, well, that's the left half of the big overbar that we just broke up. Now that's ANDed with A and not B, again with 2 overbars. Again, the first one came from the original one that was in the problem, and the second one came from the right half of the big one that we just broke up. So that was DeMorgan's theorem in action. You can break up an overbar into 2 halves, always start with the longest overbar, and if you do break it into 2 halves, you have to flip the operator from AND to or from OR to AND. Well, let's go ahead and solve the rest of this problem. If you have 2 overbars on top of something, that means that you've inverted it twice. So if you start with a 0, it becomes a 1, and then it becomes a 0 again. Or if it starts as a 1, it goes to 0, and it becomes a 1 again. So 2 overbars cancel each other out. 2 wrongs don't make a right, but 2 overbars do cancel each other out. So I can sort of just get rid of those. So I'm going to have A or B and C, and now I'm going to need to add parentheses to make it clear that that entire quantity is being ANDed with A and B bar. Now notice that only 2 of these overbars canceled. That one canceled with that one, but this overbar above the B, well, that's a separate one, and so that has to stick around. Well, we're much better. You can see we've already made a huge amount of progress, but we're not quite there yet. After all, this is our ultimate goal, A and not B. Well, let's go ahead and do some distribution here. So I'm going to have A and now the right-hand side, A and B bar, or B and C and A and B bar. Okay, a couple of things here. A and A, well, that's just A. So I have A and B bar. The second term, I have B and C and A and not B. So it's sort of like, it doesn't matter what the C and the A are, there's a B and not B. Well, it's like saying, show me a horse that is not also a horse. and show me a spaceship that is not a spaceship. There's no such thing. And so therefore, anytime that you have both the variable and its, we call complement, its not version in the same expression, that's always going to go to 0. So A and not B, or 0, just becomes A and not B. And sure enough, that big nasty original equation, which I don't think we could have simplified without De Morgan's theorem, we can now simplify it down to a much, much simpler expression.